So this is problem 5.12. A particle moves in a horizontal plane on the Earth's surface. Show that the magnitude of the coriolis force in the horizontal plane, so just the horizontal component of it, is independent of the direction of motion. So the magnitude of the horizontal force doesn't matter what direction the object is moving in the horizontal plane. And so we just start out with the definition of the Coriolis force. It's always good to do. Maybe I'll change colors here, right? So that's the definition of the Coriolis force. It's 2m omega cross v, right? Where v is just the first derivative of its position in the prime frame. And so we write all these things out, right? We've already looked at the in the previous example, we looked at what these omegas are. The rotational axis of the Earth, omega x prime is equal to 0. Omega y prime is equal to cosine lambda, times omega. And omega z prime is equal to sine lambda times omega. It's just the component of the Earth's rotational axis in the rotating frame attached to the Earth, right? And so this guy would be 0. Well, if we calculate this determinant here, this cross product, it looks like this. This is just a standard cross product. You know, this times that minus that times that. I didn't pick omega x equals 0. I just wrote out the whole thing. And we're looking at the component of f. It's asking about the component of f in the horizontal plane. So I don't need to worry about this term, because this is a component out of the horizontal plane, out of the plane on the surface of the Earth. And so I can get rid of that one. And it's just these two terms. And if I take a look at these two terms, I can say, well, the particle moves in the horizontal plane on the Earth's surface, and so that means its z dot velocity is 0 in both of these terms, because it's only got x dot and y dot because it's moving in the horizontal plane. And so that reduces my Coriolis force to this number here. Hopefully you can still see all of that, right? It's just, I've dropped out this term and all of that, and it just leaves me with this piece. It's that guy on the I hat prime. I should put a little prime there. And this is a j hat prime. Do a little better job of that, right? And that gives me these two guys. If I pull the omega z prime out, remember we just said that that's sine lambda times the Earth's angular velocity, and so that gives me this, and that just gives me an I hat. Inside this bracket is an I hat prime times y dot prime minus j hat prime times x dot prime. And so it's asking me to show that the magnitude of the Coriolis force is independent of direction. So here's the magnitude of the Coriolis force. It's just the magnitude of this quantity, which is the magnitude of this, times the square root of each of those guys squared to get the magnitude of that. But the square root of the square root of those guys is just the velocity in the horizontal plane. And so that's just the v. And notice it doesn't depend on the direction anymore. It just depends on the magnitude. It just depends on the speed. And so the magnitude of the force is the same everywhere, whatever direction it's going in. And the direction just depends on the cross product.